Hello. So this is going to cover topic 1.11 or topic 11, defining continuity at a point. Ultimately, we're going to take a look at this blue box here. There are three things that need to exist or need to happen in order for a function to be continuous at a specific x value or input value, I should say. So one, if I substitute that value into my function, there needs to be an output. It has to exist. Two, the limit from the two-sided limit, the limit from the left and the limit from the right, has to exist. And then ultimately, whatever I get for that limit has to equal whatever I get for that output. Okay. So those two things have to be equal. And number three is a really big idea. Ultimately, you can't have number three. If the first two don't exist, then the third one can't be true. Now, if we're talking about an endpoint, because that happens every so often, when we talk about an endpoint, we just need to make sure that if I'm talking about like the left endpoint, then from the right is going to equal the output. And if I'm talking about the right endpoint, then from the left is going to equal the output. So as long as I approach that endpoint and it equals where it is, then it is still continuous at an endpoint. All right. So let's take a look at some examples in a graph. So I want to know whether or not it's continuous or discontinuous, right? And then I want to use the three checklist, if you will, the three different pieces of my definition to define why it's continuous or discontinuous. So at 0, you can see that we have a vertical asymptote, all right? So we know, logic is going to tell us that we know that it's discontinuous, right? But I need you to be able to justify your reasoning. So the idea here is if it's discontinuous, then it has to fail one of these three things. And ultimately, it fails all of them, right? You could tell me it's discontinuous because f of 0 does not exist. Or you can tell me that it's discontinuous because the limit as x approaches 0 of f of x also does not exist. Because the limit from the left is going to negative infinity. The limit from the right is going to positive infinity. That two-sided limit would not exist. So you can use either of those justifications in order to tell me why it's discontinuous. Okay, let's take a look at 1. All right, so now we're looking at this value. And from the left and from the right, we're going to the same point. So the limit as x approaches 1, the two-sided limit, is going to be the y value of 1, it looks like. And then f of 1, it was defined there, is also 1. So we can say that it's continuous. And my justification, what I would like to see is that you know that as x approaches 1 of f of x is going to equal f of 1. You know those two things will be equal. All right. So now if you take a look at x equals 2, well, the limit exists, right? However, there's a hole there. So again, logic tells us, okay, well, we know it's discontinuous at 2 because there's a point missing there. However, why, right? How can I justify it? And ultimately, I would say f of 2 does not exist. Since f of 2 does not exist, you can't have the limit equal the output, right? There is no output. So at 4, okay, we're talking about these two values. We talked about in an earlier video that this is going to be a jump discontinuity. So we already kind of know that it's discontinuous because we even know the type of discontinuity that it is. But I need justification, right? So ultimately, the limit as x approaches 4 of f of x does not exist. And you can even go one step further. You can say why it doesn't exist, because the limit from the left and the limit from the right do not equal the same value, right? So the each one-sided limit is going to give you a different value in this case. That's why the two-sided limit doesn't exist. At 6, so now we're talking, if you look at 6, I have a hole, I have a point directly below it. So ultimately, this is discontinuous, right? We know it's a removable discontinuity. And this fails the third piece of our definition. We know the limit as x approaches 6 of f of x exists, and actually it's going to be the value of 6, coincidentally. And we know f of 6 exists because it's going to be where the point is. So that's going to be down here. So that's going to be at 4. So we can say the limit as x approaches 6 of f of x does not equal f of 6. Therefore, we know it's discontinuous. Okay. So now I have a series of not graphical but algebraic representations, right? Can we determine if there's any discontinuities, and we want to identify what type they are, right? So similar to the last topic. So I think there's 4 of these. Yep. So feel free to pause. You can work on these and then check your answers. Fast forward through the ones that you know how to do. But we're going to go through them one by one. So for part A, the first piece of my piecewise function is linear. I know that's continuous everywhere. The second piece is quadratic. I know that's continuous everywhere. So ultimately, I just need to know if these two pieces link up, right? So I'm going to start with the limit as x approaches 1 from the left of f of x. And if I plug in 1, that's going to be a 1 plus 4, which is 5. If I do the limit as x approaches 1 from the right of f of x, that's going to be the second piece. So I have a 1 squared minus 2, which will give me a negative 1. So ultimately, we just proved that the limit as x approaches 1, the two-sided limit, does not exist, right? And because it doesn't exist, we know that it is going to be a discontinuity at 1. And it's going to be non-removable because we defined it in an earlier video that if you have your one-sided limits, your left and your right are going to different values, then we know it's a jump discontinuity. So I know there's a non-removable discontinuity at 1, and more specifically, we know that it's a jump. Okay? So let's take a look at part B. So I have tangent of x over x. Okay? Now, what I like to do here is I'm going to write it as sines and cosines. So I'm going to say sine of x over cosine of x all over x, and I'm actually going to do a fraction over a fraction because if I multiply by the reciprocal, and I repiece this to be the sine of x over x times 1 over cosine of x. So I'm just reordering it. Multiplication is commutative. Okay, so I can reorder those pieces. Now I can take a look at this and I can kind of justify, where certain things are going to happen here. So I know that there's going to be discontinuities at 0 and everywhere where cosine of x is going to be 0, right? So if I do this, everywhere where cosine of x is 0 is going to be every multiple of pi over 2. So I'm going to say pi over 2 plus k pi, and then I need to define where k is integer. Okay. Now, we just have to define them as removable or non-removable. And I don't know if you remember, but we talked about sine of x over x. The limit does exist. The limit is actually going to be 1. We talked about that identity. Because the limit exists, but the point doesn't, we know that this is going to be removable. And then down here, we can't do anything with 1 over cosine of x. Those are going to be vertical asymptotes at those each multiple of pi over 2. So I'm going to say this is non-removable. And more importantly, those are going to be asymptotes, so we know that they're going to be infinite discontinuities. Okay? For part C, there's nothing I can really do to reduce part C. So we know that we're just going to have we're going to have vertical asymptotes. So I know I'm going to have a non-removable discontinuity at x equals -1. And more importantly, if I do that, we know that it's going to be an infinite discontinuity. Again, sometimes, they ask for, is it removable or non-removable? Sometimes they want you to be more specific. So you just have to kind of read the directions in the question or look at the multiple choice answers. I just want you to understand that all infinite discontinuities are non-removable. Okay. Next or last, if I reduce this, I have an x minus 5 over an x plus 5, x minus 5. The x minus 5s cancel. So then I have a 1 over x plus 5. So I have a removable discontinuity at x equals, well, if it's removable, I actually want to say the whole, right? So let's say it's going to be at 5, right? And if I plug 5 into my extended function, or the piece after I reduced it, I'm going to get a 1 over 10. So that's the location of the removable discontinuity. Now a non-removable is going to be at x equals -5. That's going to be where my vertical asymptote is. That's the piece of the denominator that does not reduce. And because we know it's a vertical asymptote, we also know it's infinite. So if you want to label that, you can do that as well. Okay? So the big idea here is I want you to be able to justify if a point is continuous or not continuous using this definition, right? Using those 3 criteria. So anytime that you state that something is continuous, you have to have conditions. And you need to be able to state those conditions in order to satisfy that definition. So if you ever in the future say that something is continuous, or you need to prove it, you need to say that the limit at that point is equal to the output at that point and show that all those pieces exist. Okay? Hopefully this helped. If you have any questions, let me know.